Hello friends, I welcome you all on my YouTube channel Rasayan Setu. So friends, in this video we are going to discuss previous year questions of coordination chemistry which was asked in CSIR net June 2017 exam. Okay, so let's start. Now see, this is your first question and it says choose the isoelectronic pair among the following, and we have four options A, B, C and D, or we have four complexes. Okay, so you must choose the isoelectronic pair out of these four complexes, and we have four options. Okay, and this question is coming for 2 marks. That means this is related to your part B. Understand? Okay, so let's do the solution of this question. So we must find the isoelectronic pair. So first of all, we must count the number of electrons present in each complexes. Okay, so for A complex, that is the complex of vanadium with 6 CO ligands. Okay, so now friends, in this complex, vanadium has 5 valence electrons, that is 3d2 3d3 4s2 electronic configuration. Okay, the electronic configuration of vanadium is 3d3 and 4s2. That means it has 5 electrons in its valence shell. Okay, and each CO ligand can donate 2 electrons. That means 6 CO ligands can donate 12 electrons. So that means in this complex the number of electrons are present is 5 plus 2 is equals to 17 electron. So this complex has 17 electrons. Okay, now in the B complex, the complex of copper, in this complex copper is bound with one cyclopentadienyl ligand and one CO ligand. Okay, and here its coordination state is 5C. That means this cyclopentadienyl binds with 5 sites with copper. Okay, so now on the basis of this complex, the copper has 11 electrons in its valence shell. Okay, copper has 11 electron in its valence shell, plus because it has 5 neta 5, that means it can donate 5 electrons in this complex. So this cyclopentadienyl can donate 5 electrons. So 5 plus 2 electrons can donate by 1 CO ligand, so 2. So this is a 18 electron complex. So 18 electrons present in your second complex. Now we talk about the C complex. Okay, complex C is a complex of cobalt with 4 CN ligands. So now in cobalt it has 9 electrons in its valence shell. Okay, plus 2 electrons can donate by 1 CN ligand. That means total number of electrons donated by 4 CN ligands are 8, and it has also negative charge. So negative charge is also count. So 9 plus 9, that is, it is also a 18 electron system. Okay, now in D complex, that is complex of iridium. So in this complex 1 Cl, 1 carbon monoxide and 2 triphenyl phosphine ligands are present. So now this is a now you count the electrons in this complex. So 9 electrons are present in a valence shell of iridium, plus 1 electron can donate by 1 Cl ligand, then 2 electrons can donate by this 1 CO ligand, and 1 electron is donated by each triphenyl phosphine ligand. So here also 2 ligands are present. Okay, so 9 plus 1 10 plus 2 12 plus 2 14. Okay, so this will be a 14 electron system. Understand? Okay, so this will be a 14 electron system. So on the basis of these results, you clearly see that B and C are 18 electronic system. Means in these complexes 18 electrons are present. So your B and C complexes are isoelectronic. Okay, so B and C are isoelectronic species. and this can be matched with your option number second. Option number second contains of B and C complexes. Understood? Okay, so now we move towards our next question, and see, it says these complexes are colored, or these compounds are colored. We have three compounds of cadmium, mercury and bismuth. Okay, cadmium, mercury and bismuth are colored due to, and we have four options. Okay, and this question is coming for 2 marks, friends. That means this is also related to your part B. Okay, so let's do the solution of this question. So friends, in this question we have three compounds. The first one is cadmium, sulfide of cadmium. Next one is sulfide of mercury, and the last one is triiodide of bismuth. Okay, BiI3. Okay, so this is cadmium, this is mercury, and this is bismuth. So in this condition, cadmium is present in 2 plus oxidation state, because 1s contains -2 oxidation state. Okay, so on the basis of this oxidation state of this sulfide, this cadmium is present in +2. Similarly, here mercury also present in 2 plus oxidation state. Okay, and here bismuth is present in 3 plus oxidation state, because one iodine can contain -1 charge, so 3 means -3. So this will be present in +3. Okay, so cadmium present in +2, mercury present in +2, and bismuth present in +3 in these compounds. Okay, now the electronic configuration of these ions are, so the electronic configuration of this cadmium 2 plus ions is 4d10. Okay, the electronic configuration of this mercury 2 plus ion is 5d10, and also the electronic configuration of this bismuth 3 plus ion is 5d10. Okay, so these are the electronic configurations. So now on the basis of these fulfilled electronic configurations of their d orbitals, we conclude that there is no empty d orbital present in these metal ions. Okay, and when there is no empty d orbital present in metal ion, then that means there is no dd transition present in that condition, because we know very well that for dd transition there is a must condition that at least a single empty d orbital present in that metal ion. Okay, so because of here, but here you clearly see that the fulfilled d orbitals are present. Okay, so that means in this case is no dd transitions are possible. Okay, no dd transitions are possible. Understand? Because of fulfilled d orbitals. So now on the basis of this conclusion, this first conclusion, there is no dd transition, your option number 3rd and 4 will be cancelled out. Okay, your option number, sorry, not 3rd and 4th, 2nd and 4 will be cancelled out. Why cancel out? See, because it says that option number 2nd, that dd electronic transition, because dd electronic transition are not possible. Sorry, no dd transitions are possible, and the option number 4 also contain dd transition. So option number 2 and 4 are cancelled out. Now we have left only option number 1st and 3rd. Okay, now first of all we check the possibility of metal to ligand charge transfer transition. Okay, so now friends, in coordination chemistry or in any complex, when we check that there is a possibility of metal to ligand charge transfer spectra, so we must check that that in this condition the ligand must be pi acceptor ligand. The ligand must be pi acceptor ligand. Okay, so when ligand is pi acceptor, that means in that condition metal to ligand charge transfer transitions are possible. Okay, but in this condition this sulfur and iodines are not pi acceptor ligands, and because of they are not pi acceptor ligands, that means in this compounds, there will be no possibility of metal to ligand charge transfer spectra, showing metal to ligand charge transfer spectra. Understand? Okay, so because S and iodine are not pi acceptor ligand, so there will be no metal to ligand charge transfer transitions present. So on the basis of this conclusion, your option number 3 will be also cancelled out, which says metal to ligand charge transfer transitions. Okay, so ultimately we have only option number first, which states ligand to metal charge transfer transitions. Okay, so that means in this complexes, in this compound, the colored are due to ligand to metal charge transfer transitions. We cancel out all rest of the 3 options. Okay, so that's why we conclude that in these compounds, ligand to metal charge transfer transitions are present, and color of these compounds is due to these transitions, that is ligand to metal charge transfer transitions. Okay, so it is your option number first. Your option number first is the correct answer for this question. Understand? Now we move towards our next question, and see, it says the relative rates of water exchange for the hydrated complexes of nickel 2 plus, vanadium 2 plus and chromium 3 plus ions follows the trend, and we have 4 options. Okay, so friends, in this question we have a water exchange reactions of this nickel, vanadium and chromium compounds. Okay, and you must find the rate of the water exchange reactions for these complexes. Okay, the order of the water exchange reaction rate in these complexes. Understand? Okay, and this question is coming for 2 marks. That means it is also related to your part B. Okay, so let's do the solution of this question. Now first of all, we get a small idea about water exchange reactions. So what is water exchange reaction in your coordination chemistry? So in water exchange reactions, it involves a replacement of water ligand with water in solution. Okay, so when there is a presence of a hydrated complex of any metal ion in water, then in this condition there will be a exchange of water ions between a solution, between water molecules of solution and a water ligand of the complex. So this type of reactions are known as water exchange reactions. Okay, so this is a brief idea about water exchange reaction. So I can write here that in water exchange reaction, it involves replacement of a water, okay, replacement of a water ligand. This is known as coordinated ligand, coordinated water with water in solution. Or you can say bulk water. So it is a general statement for your water exchange reaction that it involves the replacement of water ligand, that is coordinated water. So we use the term ligand for the coordinated water, and we use bulk water for the water present in solution. It will be shown by this general example. See, suppose we have a complex of metal ion in which which is a hydrated complex, okay, and it will be react with this water. This is a water present in solution. So there is a replacement of one of the H2O of this complex ion by this H2O. Okay, see, this will be N minus 1 and this will be H2O star plus H2O. So this is a general water exchange reaction. Okay friends. Now in this question they was asking you about the order of the reaction rate for the different complex ions. In this question we have three complex ions, that is nickel 2 plus, vanadium 2 plus and chromium 3 plus. Okay, so we have chromium 3 plus, nickel 2 plus and vanadium 2 plus ions, and you must find the order of the water exchange reaction rates in these complexes. Okay friends. Now first of all, what factors can influence the reaction rate, water exchange reaction rate? So the first factor which we use, that is the charge on the metal ion. The first factor which we used for finding the rate of the water exchange reaction between these metal ions is the charge present on that metal ion. Now how can we relate the charge present on metal ion with the water exchange reaction rates? So friends, there is a concept that says that when charge is high on metal ion, when charge is high on metal ion, that means they are highly charged. Okay, so that means that they exchange their water more slowly. This is a concept. When charge is high on metal ion, they will exchange their water more slowly. Okay, so on the basis of this statement we clearly see that chromium has 3 plus and nickel has 2 plus in its okay, chromium is 3 plus oxidation state and nickel present in 2 plus oxidation state, and we say that when charge is high on metal ion, they will exchange their water slowly. Okay, so in between these metal ion, in between chromium 3 plus and nickel 2 plus metal ion, the reaction rate is high is for nickel 2 plus, because it has 2 plus charge, vanadium also has 2 plus charge and chromium has 3 plus charge. So it will so chromium 3 plus will exchange their water more slowly compared than nickel 2 plus and vanadium 2 plus. Okay, so I can write this concept here. See, it says it is mainly influenced by charge. Now highly charged metal aquacations exchange their water more slowly. So on the basis of this statement we conclude that complex containing chromium 3 plus exchange their water slowly. So out of these three complexes, the least rate is for chromium 3 plus complex. The least rate for water exchange is for chromium 3 plus complex. Okay. Now, when charge is same on both metal ions, then what factors what factor decides the water exchange reaction rate? So when we have a condition in which the charge is same on the metal ions, then in this condition the deciding factor is the CFSE of that metal ion. The deciding factor is the CFSE of that metal ion. And how can we relate the CFSE with that water exchange reaction rate, that the complex with high CFSE exchange their water more fastly. The complex with high CFSE exchange their water fastly. Okay. So first of all we conclude that the least rate is for chromium 3 plus. Now in between nickel 2 plus and vanadium 2 plus, because they both has same oxidation state, same charge. So in these ion we first conclude their respective CFSE, and after their calculation we decide that what ion shows more water exchange reaction rate. Okay. So now we have a formula of CFSE. We know that in coordination chemistry the formula of CFSE is minus 0.4 P plus 0.6 Q del O plus M into P. Okay. Here M is number of electron pairs present in that metal ion, P is number of T2G electrons, and Q is number of EG electrons. Okay. So first of all, in the case of vanadium 2 plus, the vanadium 2 plus. Okay. So for vanadium 2 plus, its electronic configuration is 3d3. So it has 3 electrons in its T2G lower energy T2G orbital and 0 electrons in higher energy EG orbital. Okay. So on the basis of this data, the value of CFSE for vanadium 2 plus ion is minus 1.2 del O. We conclude it. Okay. Because here the value of M will be 0. There is no electronic pairs are present in this metal ion. Okay. And similarly in case of nickel 2 plus, the electronic configuration of nickel 2 plus is 3d8. Okay. So that means it is T2G6 EG2. So its value of CFSE will be minus 1.2 del O plus 3p, because it has 3, number of M is 3, number of electrons pairs are 3. Okay. So the value of CFSE of vanadium 2 plus is minus 1.2 del O, but the value of CFSE of this nickel is minus 1.2 del O plus 3p. So it means the value of CFSE is high in case of nickel 2 plus than vanadium 2 plus, and we say that the complex with high CFSE exchange their water fastly. Okay. I can write here that complex with high CFSE exchange their water fastly. So now it means the highest rate is for nickel 2 plus. The highest rate is for nickel 2 plus, then vanadium 2 plus, and then chromium 3, because chromium 3 plus has least rate out of these 3 complexes. Okay. So first of all, when the charge is different on metal ion, then we use the concept of charge. Okay. Oxidation state is different, that means we use the concept of charge present on that metal ion. But when oxidation state is same, then in that case we use the concept of CFSE. Okay. So now we get this order, the order of the water exchange reaction rates, and this follows A is greater than B is greater than C, because A is nickel 2 plus, B is vanadium 2 plus, and C is chromium 3 plus. So on the basis of this conclusion, your option first is the correct answer. Okay friends, option first is the correct answer for this question. See once again the complete solution of this question. I hope you understand it. Okay friends. Okay, so now we move towards our next question, and see, it says a copper second complex having distorted octahedral geometry shows an absorption band at 625 nanometer. Given spin orbit coupling of the complex as -6 to 5 centimeter inverse, the mu effective, that is spin only magnetic moment in Bohr magneton is, and we have 4 options. Okay friends, and this question is coming for 4 marks. That means this is related to your part C. Okay, so let's do a solution of this question. Now friends, when you carefully observe this question, so it contains a complex of copper second having distorted octahedral geometry. So friends, if you remember, there is a question asked in your June 2016 CSIR net exam, and in that question they was asking about the expression of magnetic moment which is responsible for a greater value of magnetic moment of copper second complex than 1.73. Remember, in June 2016 exam they will ask you a formula, and in this paper they will ask you a question. They will ask you a question related to that formula. So in June 2016 they was ask you a formula which is responsible for the higher value of magnetic moment than 1.73, and in this question they can relate that formula in this question. Okay, and so if you remember friends, according to that question we conclude the formula. The formula says that mu effective is equals to mu spin 1 minus alpha lambda upon del. This is a formula, and this is responsible for the higher value than normal value, for the higher value of magnetic moment than its normal spin only value. So we use this formula in copper second complex. Okay, and here the mu s can be find out by this under root n into n plus 2 simply. Okay, and in the case of copper second, it will be, its value will be under root 3, which is nearly equal to 1.73 Bohr magneton. Here lambda is a spin orbit coupling constant. The lambda is spin orbit coupling constant which is given in this question, that is 625 centimeter inverse. This is your spin orbit coupling constant. Spin orbit coupling constant. Okay, and here alpha is depends on the ground term. Alpha is equals to the value of 2s plus 1 in your ground term of that complex, and in case of copper 2 plus complex, its ground term will be 2d. So its value of 2s plus 1 will be 2. So its value of alpha will be 2. Okay, alpha is equals to 2s plus 1, and this 2s plus 1 is related to a ground term of that particular complex ion. And in this question they will give you copper 2 plus metal ion, and for copper 2 plus metal ion its ground term will be 2d. So that means the value of 2s plus 1 is 2, so the value of alpha is also 2. Okay, and the value of delta will be equals to 1 upon lambda. The value of delta is equals to 1 upon lambda, and now here its value will be 1 by 625 into 10 to the power 9 meter, because it is in nanometer. So it will be 1 by 625 into 10 to the power 7 centimeter inverse. When we convert nanometer to centimeter, this is a conversion. So the value of del will be 10 to the power 7 upon 625 centimeter inverse. Okay friends, so now we have all the values, that is mu s under 1.73, alpha that is 2, lambda that is 625 centimeter inverse, and del 10 to the power 7 upon 625 centimeter inverse. You can put all the values in that formula and we will get our answer. Okay, so when you solve this complete solution, you will get the value of mu effective, that is nearly equals to 1.81 Bohr magneton. Okay, so when you solve this equation, you will get the value, that is 1.81 Bohr magneton nearly. Okay, so and this is your option number second. Option number second is the correct answer for this question. Understand? Okay. Now we move towards our next question, and see, it says, consider the following statements for octahedral complexes, and we have three complexes A, B and C, and we have four statements, and the correct statements are, so you must find the correct statements after of these four statements for these three complexes A, B and C complexes. Okay, and this question is coming for 4 marks, that means it is also related to your part C. Understand? Okay friends, so let's do the solution of this question. Okay friends, now they will ask you the correct statements, and we have three complexes. The first complex is the complex of chromium. All complexes are chromium complexes. Okay, difference is the ligands. This will be 3 minus. Okay, this will be 3 plus. These complexes are given. Now first of all, the common thing you see in all these three complexes, that in all these complexes, chromium present in +3 oxidation state. Chromium present in +3 oxidation state, and for chromium +3 oxidation states, its electronic configuration is 3d3 4s0. That means it has 3 electrons in its d orbital, and 3 electrons means in lower T2g orbital it has 3 electrons, and in higher Eg orbital it has 0 electrons. So the electronic configuration of this chromium 3 plus ion is T2g3 Eg0. Okay friends, now that means on the basis of this electronic configuration, you conclude that T2g orbital is symmetrically filled or electronically non-degenerate orbital. Okay, so T2g orbital is symmetrically filled. And we know very well that when T2g orbitals is symmetrically filled, that means there will be no John-Taylor distortion present in that molecule, in that complex ion. For showing John-Taylor distortion, the must condition is either T2g or Eg orbitals are unsymmetrically filled. Okay, so when Eg or T2g orbitals are unsymmetrically filled, that means there is a presence of John-Taylor distortion in the geometry of that complex molecule. But when T2g or Eg orbitals are symmetrically filled, that there will be no John-Taylor distortion present in the geometry of that complex ion. So because here T2g orbital is symmetrically filled, or we can say that electronically non-degenerate orbitals, so all of them not show John-Taylor distortion. So all of them not show John-Taylor distortion. So this is the first conclusion. Okay, so all of them not show John-Taylor distortion. So on basis of this conclusion, your statement D is incorrect, which states that all of them show John-Taylor distortion. But because of T2g orbitals are symmetrically filled in all these complexes, because all complexes are containing chromium 3 plus metal ion, So all of them don't show John-Taylor distortion. Okay, so option D incorrect. Now friends, when you carefully observe the remaining options, when you carefully observe the options first, second, third and fourth, here we conclude that option D was incorrect, and according to this question you must find the correct statements. Statement D is incorrect. We conclude that statement D is incorrect, and option number second, third and fourth contain this D statement. So that means the combination, so that means these combinations are also incorrect, which so that means all combinations which contains the statement D was incorrect combination. And in this question the option number second, third and fourth contains D statement. So that means automatically they will be cancelled out. Okay, so only left option is option number first. Okay, so option first, which contains A, B and C statements, are correct. So option first is the correct answer, that contains A, B and C statements. Okay, and they says that their DD transitions are these. Okay, this is the correct. The spin only magnetic moments are same because all contains chromium 3 plus ion, and two of them have optical isomerism. Okay, because option number B and C show optical isomerism. B and C shows optical isomerism. So the only thing is that you observe carefully. So when you observe carefully, we conclude that option because of option second, third and fourth contains D option, which is incorrect. So these sets are automatically cancelled out. So we have only option number first, which contains statement A, B and C, and these are correct statements. Understand? Okay. So now we move towards our next question, and see, it says the mu effective of this complex, that is spin only magnetic moment of this complex, changes with temperature with the involvement of two electronic states. The states are, and we have four options. Okay, so the spin only magnetic moment of this this complex changes with temperature. Okay, and you must find the involvement of two electronic states. Which electronic states are involved in this behavior of that complex. Okay, and this question is coming for 4 marks. That means it is also related to your part C. So let's do the solution of this question. So we have this complex in this question. So in this question, the iron present in +3 oxidation state, and for iron +3, its electronic configuration is 3d5. Its electronic configuration is 3d5. Okay, and for 3d5 electronic configuration, we know very well that we have two conditions, that is 3d5 low spin condition and 3d5 high spin condition, and you must find the electronic terms associated with this high spin term and low spin state. Okay, the terms associated with this high spin state and this low spin state. Okay, in this question, so first of all we must find the term related with high spin or related with low spin, then we find for high spin. Okay, so for 3d5 low spin state, for 3d5 low spin states, the electronic configuration for 3d5 low spin will be T2G5 Eg0. Okay, that means all 5 electrons are present in lower T2G orbital. Okay, and for this electronic state, the ground term is, we know the formula for ground term, that is 2s plus 1l. Okay, So for 3d5 low spin state, this is the condition. So first of all, here the value of S will be half, because only a single single unpaired electron present, so its value is S is equals to half. So the value of 2s plus 1 will be 2. Okay, the value of S is half, so half into 2 1, 1 plus 1 2. And here the value of L is the sum of azimuthal quantum numbers of all electrons, so it will be 3. The sum of the all azimuthal quantum numbers of all electrons are 3, and the term associated with L is equals to 3 is F. So that means its ground term will be 2F, and this ground 2F term will further split into 3 terms. That is, the splitting of this ground term will be into 2 T1G plus 2 T2G plus 2 A2G. So this will further split into these ground terms. Okay. Now for 3d5 high spin, 3d5 high spin. For 3d5 high spin, it will be T2G3 EG2. So similarly, we find ground term for this electronic configuration, and for this electronic configuration, the ground term we get is 6s, and S is singly degenerate. Okay, the F term will be triply degenerate in 2 T1G, 2 T2G and 2 A2G, but this S is singly degenerate, and which is 6A1G. Okay, so it will be triply degenerate, it will be singly degenerate. So that means on the basis of this conclusion, we get the ground, the states associated with the high spin and low spin states. So the states which are associated with low spin is 2T2G, this one, according to your options given in this question, and the states which are associated with high spin is this 6A1G. Okay, so states are low spin 2T2G and high spin 6A1G. These are the states associated with your low spin and high spin electronic configuration of this 3d5 electronic configuration, or this 3d5 state, okay, of that iron plus 3 metal ion. And this is your option number first. Your option number first is the correct answer for this question. Understand, friends? Okay. Okay. Now we move towards our next question, and see, it says match the items in the 3 columns, and we have 3 columns. First column contains complex, second color, and third one is lambda max, and you match these 3 columns with each other, and this question is coming for 4 marks. That means it is also related to your part C. Understand? Okay. So let's do a solution of this question, friends. Okay, so now first of all, we match the lambda max with complex ions, and after that we match the color with complex ion. Okay, so for lambda max, first of all you must find the order of CFSE of that, because in all these in this question all complexes, that is A, B and C, are octahedral complexes C. Okay. Okay, and here the order of delta O is order of del O for different ligand is, see, the highest order of delta O is for ethylene diamine, then for NH3, and the least value of delta O is for H2O. Okay, friends. So friends, this is nothing but a ligand field strength. The value of delta O is nothing but a ligand field strength, or you can say the spectrochemical series for ligand. You get these values by spectrochemical series for the ligands in coordination chemistry. Okay, so this is the ligand field strength order. So on the basis of this, the order of CFSE is, so order of CFSE is, highest order is for the complex C, because it contains ethylene diamine. Then for complex B, because it contains NH3. Then least order for CFSE is for complex A, okay, which contains H2O. So it is a crystal field stabilizing energy. So that means it is a order of absorption energy. It is a order of energy in these complex ions. Okay, so that means highest energy absorption is present is for the C complex. Okay, so means highest energy absorption in C. In complex C, which contains ethylene diamine, because according to this order of CFSE. Okay, so that means when we know there is a relation between the energy and wavelength. Here lambda max is a wavelength, that they are inversely proportional to each other. When there is a high energy, there will be the low wavelength. Okay, so that means highest energy absorption in C. So that means it has lowest value of lambda max. When highest energy absorption is present in C, that means it leads to the lowest value of lambda max. So it will leads to lowest lambda max. And for A, it has lowest energy absorption, so that means it leads to highest lambda max. So C leads to lowest lambda max and A leads to highest lambda max. And in this question, the highest lambda max is 675, which is X, and lowest is 565, which is Y. So that means your C relates to Y, and your A relates to X, and your B relates to Z. Okay, so that means C relates to Y, B relates to Z, and A relates to X, according to this conclusion. Okay, understand friends, how can we relate C to Y? On the basis of the CFSE, and on the basis of CFSE, we find the energy absorption value, and we can relate the energy absorption value with lambda max. So highest energy absorption leads to lowest lambda max, and lowest energy absorption leads to highest lambda max. So on the basis of this conclusion, we can relate C to Y, B to Z, and A to X. Okay, so on the basis of this, so the order of energy absorption is, order of energy absorption is A is less than B is less than C. Least order is in A, then for B, and then for C. Now after this we talk about color. So friends, in coordination chemistry, the complex the color of the complexes is a complementary color of absorbed light. In complexes, color of the complex is the color of the complex which is shown by that complex is a complementary color which is absorbed by that complex, okay. And we must find the complex on the basis of the color wheel. Okay, so first of all I write here that what I say that in complexes, in coordination complexes, color of the complex is a complementary color of absorbed light. And the relation between this absorbed light and this complementary color can be shown by the color wheel. So color of the complex can be predicted on the basis of color wheel. Okay. So complex's color is the complementary color of absorbed light. And what is the relation between this absorbed light and this complementary color which is shown by that complex is we can find out by the color wheel. Okay. So here this is a color wheel. I can draw here. I can draw the color wheel. On the basis of this wheel, you simply find out the relationship between absorbed light and the complementary color. Orange. Okay, this is orange. So this is a color wheel for coordination complexes. Opposite colors are complementary colors. See, the complementary color of red is green and the complementary color of green is red. So that means when a red color red color is absorbed by the complex, it will show you a green color because it is a complementary of red. Similarly, when a green color light is absorbed by the complex, so this complex can show red color because they are complementary to each other. Similarly, this yellow and purple are complementary to each other, and this orange and blue are complementary to each other. So now on the basis of this color wheel, we conclude that blue color complex absorbed light is orange. So the complex with blue color can absorb orange light. Similarly, green color complex can absorb red light and violet color complex can absorb yellow light. Understand? Because blue, green and violet can given in this question. So first of all, you must find that what light is absorbed by that complex ion. So for blue, the absorbed light is orange. For green, the absorbed light is red, and for violet or purple, the absorbed light is yellow. Now, what is the energy of these colors? We know that for visible region, the order is VIB GYOR. So this is a increase in lambda, and this is a order of decrease in energy. So the highest energy is for violet and the lowest energy is for red, and the highest wavelength is for red and lowest wavelength is for VIBGYOR. Now on the basis of this conclusion, we get the energy order of the absorbed light. So energy order of absorbed light is. The highest energy is for yellow, then for orange, and least for red. Okay, so that means we also find the energy order in our previous page. That is the C, and this is related for B. The highest energy is for C, so that means it is related to your yellow color. And then energy related to B, it means it is related to your orange, and the least energy is for A, and that means it is related to your red color. So we must so we also find the order of energy in our previous page. Okay, so that means the complementary color of yellow is violet or purple. The complementary color of orange is blue, and for red it is green. Okay friends, now this is the color shown by that complexes which is given in your question, and these are the absorbed light by these complexes. So we can also find the relationship between we can also match the pairs between the complex and the color ion. Okay, that means C can show violet color, B can show blue color, and A can show green color. And in previous page we find the match between the lambda max and that complex ion. That means your A related to your second, which is green, and this is also related to a lambda max, that is X. Similarly, B related to your first, that is blue, and value of lambda max is Z, and C related to third, that is green, which is related to your Y. So we can match all of these three columns. Okay, A related to second one, and this is related to X, B is related to first with Z, and C related to third with Y. Understand friends? Okay, so see once again, this is your color wheel. This is an important concept friends, this color wheel. These are the opposites, one are complementary to each other. Red and green are complementary to each other, yellow and purple are complementary to each other, orange and blue are complementary to each other. Means when absorbed light is red, the color shown is green. When absorbed light is purple, color shown is yellow. When absorbed light is blue, color shown is orange. And oppositely, when absorbed light is green, color shown by red. Absorbed light is yellow, color shown is purple. And absorbed light is orange, color shown is blue. Okay friends, I hope you understand it. ओके फ्रेंड्स, सो ये थे आपके कुछ क्वेश्चंस कोऑर्डिनेशन केमिस्ट्री के जो CSIR नेट जून 2017 पेपर में आपसे पूछे गए थे. ओके, आई होप आपको सारे सॉल्यूशन समझ आए होंगे. और फिर भी किसी भी तरह की डिफ़िकल्टी आती है तो कमेंट सेक्शन में आके ज़रूर पूछिए. सो थैंक यू फ्रेंड्स, थैंक यू फॉर वॉचिंग.